Okay, good morning everyone. Thank you for attending today's session. So my name is Priyal Daya. I'm a PhD student at St. Mary's University, supervised by Dr. Jacob Hanley, who runs the Ore and Fluids Laboratory in the department. My project is titled Melt Inclusions Associated with Archean Volcanogenic Massive Sulfide Deposits, and we're collecting some of the first constraints on the pre-eruptive metal and volatile contents of magmas. Just a little bit about me. I'm originally from South Africa, where I did my undergraduate and my master's degrees and moved to Canada for my PhD. Thank you to all our research partners and funding partners for this project. It's really helpful to have you collaborate with us. So some of the key objectives for my research project is to establish that methods and approaches that are currently used to study melt inclusions, typically for younger magmatic hydrothermal ore systems, can also be applied to Archean VMS systems. And I'm also trying to determine the chemical characteristics of melt inclusions to understand how metals are supplied to these VMS deposits. I'm also trying to examine the spatio-temporal variations of the silicate melt inclusion chemistry from both metal-fertile and metal-barren volcanic units to understand the evolution of VMS deposits in the Abitibi Greenstone Belt. For the first bit of the talk, I will be presenting on the chemical characteristics or compositional data that I've already collected for silicate melt inclusions. And then I'll be handing over to Jacob, who will be talking about the geochronology data that we have just collected. So as I mentioned, my study area is the Abitibi Greenstone Belt, and I have two main VMS deposits that I'm looking at. They are the well-known Kidd Creek and Laron-Piana VMS deposits, which are located in the Kidd Munro and Blake River assemblages, respectively. I am also looking at silicate melt inclusions that have been collected from barren units within these same assemblages, and also silicate melt inclusions that are hosted in barren assemblages that bracket these productive assemblages, for example, Deloro, Tisdale, and Porcupine assemblages. So this just shows a stratigraphic column for the Doyen Bousquet Laron mining camp. For my sample suite, I have included units from the Hebercore Formation, which underlies the Bousquet Formation. And I also have various samples from Unit 2 lithologies, which are the tholeiitic to felsic sills, Unit 5.2, which is the rhyodacite rhyolite, and I have also samples from the Unit 5.3, which is the main host rocks that host the ore bodies in the Laron-Piana VMS deposit. So the approach that I've been using is a very detailed melt inclusion petrography study, where I look at buried melt inclusions in transmitted light in the zircon. I map these out so that I can do laser ablation ICP-MS on them. And then I also have been analyzing melt inclusions that are exposed in the zircons using scanning electron microscopy, and then obtaining CL images to identify different zircon growth domains, for example, xenocrysts, anticrysts, and autocrysts, and to tie this all together to understand how or when these melt inclusions formed relative to the zircon formation. We are collecting data, geochronology data using CID terms to resolve these zircon growth domains. And in this figure, you can see that most zircons show at least two growth zone domains with distinct luminescence. And the silicate melt inclusions are hosted in more than one zircon domain within single samples. The zircons themselves contain various types of inclusions. For example, you have your silicate melt inclusions, and then you have other trapped phases such as apatite quartz, biotite, various oxides, as well as some sulfide inclusions that we have seen containing chalcopyrite and pentlandite. And the silicate melt inclusions themselves are very well preserved, considering they are hosted in Archean aged rocks. And the silicate melt inclusions hosted in zircon are unhomogeneous, there's a typo there, and contain a mixture of, for example, quartz, alkali feldspar, albite, and epidote. So looking at the major elements, major elemental composition of the silicate melt inclusion, I have just plotted the compositions on the total alkali versus silica diagram, and you can see that there's a very large scatter of the silicate melt inclusion compositions on these diagrams. I just realized that I've not mentioned that for today I'll only be discussing results from the Bousquet formation and not talking about the Kidd Creek deposit. So you can see that some of the silicate melt inclusions actually have very low silica contents, and these outliers could possibly be due to accidentally trapped phases in the silicate melt inclusions, for example, apatite, oxides, biotite. But if we look at the data without these outliers, we can see that there's actually a compositional trend from rhyolitic to trachytic compositions, and this trend from subalkaline to alkaline could possibly be due to some magma mixing or contamination. And then also looking at the bulk rock compositions, which lie around the rhyolitic compositions, you do not observe this widespread of compositions from the bulk rock as you observe from the, looking at the silicate melt inclusions. And then comparing the laser data to the SEM data, we can see that the compositions of silicate melt inclusions are consistent using these two methods. This is a very small data set that we had from the SEM, but you can still see a similar trend in composition with the data. So now looking at some metals from bulk silicate melt inclusions, I have plotted 3 ternary diagrams here. This top ternary diagram is of the silicate melt inclusions that contain a base metal total, so copper plus lead plus zinc, less than 100 ppm. And you can see that the majority of the data points fall into the zinc corner of the ternary diagram, and this is consistent with silicate melt inclusion data that has been plotted from the Laurent Penna VMS deposit. And these compositions most likely represent the true silicate melt inclusion compositions, meaning that they are not contaminated with sulfides, whereas the bottom 2 ternary diagrams, these are the total base metals, copper plus lead plus zinc, greater than 100 ppm and greater than 1,000 ppm. And you can see a lot of scatter towards the copper corner and lead corners of the ternary diagram. And the possible explanation for the silicate melt inclusions falling around the lead corner of the ternary diagram could possibly be due to trapped lead sulfides. For example, we have come across an example of galena that has been trapped and associated with the silicate melt inclusions. And then for silicate melt inclusions that plot around the copper corner of the ternary diagram, this could be due to trapped copper sulfides. And again, we also see some silicate melt inclusions that are associated with chalcopyrite. Another reason for such silicate melt inclusions having high lead values is possibly due to the degassing of copper early on in the magma system. So when copper gets removed, then lead will saturate. So this diagram just shows that a few of the metals associated with the silicate melt inclusions. And you can see from metals such as cobalt, nickel, molybdenum, and antimony, there's a general increase in the metal content as you move from Unit 1, which is the Heber formation, through upwards in stratigraphy. And there's also a widening in range of the metals, the metal contents. The really high values where they go into the thousands of ppm could also be due to trapped sulfides in the silicate melt inclusions. And then the lower metal values in Unit 5.3 are possibly due to magmatic degassing prior to ore formation. And then with zinc and lead, we note that these metals actually decrease from Unit 1 to higher stratigraphic units. And looking at the bulk rock compositions, we can see that not all the bulk rock compositions are even close to the metal compositions that are observed in the silicate melt inclusions. So the silicate melt inclusions provide a wider range in metal contents compared to that of the bulk rock. Again, I have just plotted the copper and zinc values, and I've compared it to a porphyry copper silicate melt inclusion data from porphyry copper deposit. This one is from the Bingham porphyry copper deposits, as well as from two barren granites that are associated with porphyry copper deposits. And again, you can see that the silicate melt inclusion data from these deposits versus the Bousquet units does show an overlap, even though the range of the metal concentrations in the silicate melt inclusions from the Bousquet units are wider and are slightly higher concentrations than the silicate melt inclusions from the porphyry copper deposits and the barren granites. But they more or less show an overlap. And I have also just compared these to silicate melt inclusions from the from barren units within the Kidman Row and Deloro assemblages. And again, you do see quite an overlap of the melt inclusion data with those of the Bousquet units. So just to highlight some key points so far, integrating CL imaging with silicate melt inclusion petrography will allow for temporal constraints on the melt compositions. To do this, we need to use CID terms or shrimp to avoid silicate melt inclusions that are tied to inherited zircon domains. And zircon chemistry paired with silicate melt inclusion chemistry is needed to evaluate parameters related to magma evolution, for example, thermometry, fractionation, recharge, and oxygen fugacity. And then the bulk composition of the silicate melt inclusions from the Bousquet formation ranges from rhyolitic to trachytic, and this requires magma mixing or contamination to account for silicate melt inclusions for the variation of these compositions within single lithologies. And then transition from Hebercore to lower Bousquet accompanied by a decrease in lead and zinc and increase in copper, molybdenum, and tin, antimony, which are typically arc signatures, but also cobalt and nickel, which are alkalic arc. And there's a wide range in metals which reflects sulfide saturation. And there's also high copper, molybdenum, and antimony, which remain sustained from lower to upper Bousquet. The silicate melt inclusions in the lower Bousquet, which are tholeiitic sills, show a larger range in copper and higher overall concentrations compared to that of units 5.3, which host the main ore units, ore zones, and then lead lead is higher in the upper Bousquet formation. And this suggests that the metals removed from the main magmatic system via degassing, possibly, and copper from the upper Bousquet, or sulfide saturation. And then lead sulfide saturation is also observed in the upper Bousquet. So silicate melt inclusions in the Bousquet rhyolites have notably higher copper than input magmas in large copper porphyry and barren granitoids, but they are comparable to silicate melt inclusions in barren Kidd-Monroe and Deloro rhyolites. And all of these are productive assemblages enriched in these metals, even possibly distilled to mineralization. So now I'll be handing over to Jacob, who will be talking about some preliminary geochronology data that we have. Thank you.
Thanks, Priyal. Just a comment that the melt inclusion literature sort of stops at about 600 MA. So the data that you're seeing today are sort of the first data in the Archean and also the first data for VMS systems globally. So it's challenging rocks to work with. So thanks, Priyal, for the intro slides and also the summary of all of your first data coming out from the Bousquet. I just want to follow up on a few key items. One is that this theme of sulfide melt saturation seems to be pervasive in all of the rocks that we're looking at from the Bousquet sequence. And that means that the rhyolites were sulfide saturated at the time of entrapment. And when we look at the chemistry of those sulfides, which are shown in this diagram in the red patterns, that's absolute abundance in ppm. ppm is missing from the y-axis there. For the upper and lower Bousquet, the lower Bousquet in red and the upper Bousquet in green, there are some fundamental differences in the sulfide chemistry. The main differences are that the lower Bousquet shows this elevated copper and perhaps tellurium, whereas when you shift into the upper Bousquet, the copper drops and the arsenic and antimony go up. And so the question becomes, if you start looking at the chemistry of ore zones within these sequences, and I'm going to just plot, if just you look at the LaRonde gold-rich ore, the very aluminous ores at LaRonde, which are carrying the highest gold tenors, the question becomes, which of these magmas do you actually associate with gold enrichment? Because the chemical or metallogenic character of those ores appears to require input from both lower and upper Bousquet. And so I guess leading forward, can you actually link individual deposits to the accessory metal endowment that we see in magmatic sulfides? So that's one additional point. The second is that we've gone back and started to look a little more carefully at the geochronology that is published for the Bousquet rocks. And this is showing a summary at the top of all of the data available for the Bousquet formation in the empty rectangles. This is ID TIMS data. And then below that, data that we've collected on the MIC, the Mouchla intrusive complex, as well as the upper and lower Bousquet formation. And these data were collected using the Earth time tracer, not only again on the volcanic rocks, but also on the MIC rocks. There's a paper will be coming out later this year by a PhD student at St. Mary's, Kevin Nedley, that looks carefully at the MIC rocks, and he's identified evidence that these magmas started crystallizing at very deep, 25 to 40 kilometers. Prior to ascent, they've degassed, and that the Musca and the Doyon stages of the MIC were actually coeval. So this requires to have multiple magma chambers operating simultaneously in order to explain the ID TIMS data for those rocks. But then when we look at the Bousquet, the new data that you see in red and yellow at the top of the diagram there actually brackets appropriately all of the respective ID TIMS ages for the MIC. But what's fascinating is that the earliest rocks in the Bousquet, the Unit 2s, actually predate any of the rocks of the MIC by approximately 50 to 100,000 years. So this means that The Bousquet magmas are coming in, they're sulfide saturated, and then you can generate the complete sequence of the MIC rocks through mixing of these two respective end members, and we now have a bracket in terms of age that restricts, brings us back from about a 5 to 6 million year window to a less than 2 million year window for the emplacement and eruption history for the Bousquet. So that means that we have about 2 million years or less to work with to generate the gold endowment. And I think an interesting comparison in the lower right is if you look at the ore duration versus total gold tonnage in porphyry systems, and we take a look at the total gold endowment of the entire DBL camp, which is about 500 tons of gold, you can easily achieve supplying all of that gold to a VMS system like La Ronde in that 2 million year window. You have a couple of different recipes. You could do that with a conventional copper porphyry system. Those are the data shown in green in the plot in the lower right. There are also gold-rich porphyries that have lower copper endowment that produce very high endowments of gold in much shorter timescales. So again, it's reasonable to provide all of that information, all of that gold from a porphyry-like system in this 2 million year timescale. The question is how much magma is needed for the DBL camp. Clearly, the system was sulfide saturated. It was sulfide saturated at depth. And based on the results from the MIC that Kevin has collected, it's a big magmatic system operating there. So I think going forward, one of the key questions will be trying to reconcile the metal concentrations in melt inclusions with the absolute amount of magma that would be required to produce the metal endowments in the camp. And then work in progress. Priyal is continuing working on the Kidd Creek VMS system and the barren assemblages. And really the next step will be to reconcile the zircon geochronology and the zircon trace element chemistry with the melt inclusion data to see if we can recognize changes in metal composition within individual units throughout geological time in the context of the other types of data that we've collected. Thanks.
Great, thank you, Dave. JC, we don't need to use the microphone, but
How do we speak up? How you recognize that they are actual melt? What's the physical state? Are they still glassy, crystallized? What's your proof that they are actual melt?
Priyal can answer this.
So when we first did the study of the melt inclusions, like the first preliminary study, a number of inclusions that are over, well, some of the inclusions are very big in size, and they're not glossy. They, like I said, they were unhomogenized, so you can see various phases in that state. And it's only the really tiny inclusions that are less than 2 micrometers that are maybe glossy. But what we have also done is we took half the zircon separates and we've annealed some to, I think it was 900 degrees Celsius for 6 hours to anneal them. So we have comparisons between homogeneous silicate melt inclusions and unhomogeneous silicate melt inclusions.
other questions? Is there any way to study similar, because all your melt inclusions are on zircons?
Yes.
Is there any way to look at the mafic components of these successions?
Yeah, we did get some separates attempted from some of the mafic units. We have some bedelliite, but the grains are so tiny that we can't work with them. So it's an issue is that we can't recover the mafic record as easily because just they're zirconium poor rocks and the grains are super small. Yeah.
I was wondering, how do you get the sulfur saturation? Do you get it through contamination or do you get it through
One possibility is that when there could be degassing of like copper out of the system, and so other sulfides could saturate. In terms of the initial saturation, I think we're still trying to figure that out. Why was the magma in the first place so saturated in sulfides? I don't know if Jake wants to add to that.
Yeah, I mean, it could be, as Priyal said, degassing. That's, if it's removing water, then your sulfides can stabilize, but this, if it's done at high FO2, can also cause them to dissolve. So where the sulfides are coming into the story is not totally clear yet, but it is very deep. I mean, we see these trapped in melt inclusions in the cores of zircons that have grown at 25 to 40 kilometers. So we're down at this TTG production window, and these zircons are coming up. But they're coeval with the magmas. They're not xenocrystic. They're giving us MIC ages.
All right. Anything else?
Yeah, Ross.
Yep.
As a porphyry geologist, and you talk about sulfide saturation, are you talking about reduced sulfide, or are you talking about oxidized sulfide?
I think mainly, well, at the moment we're talking about saturation of like purite-like sulfide compositions.
So NSS type stuff.
Yeah, but there is also in the MIC and in inclusions in the MIC, there is coeval anhydrite. So actually the FO2 is probably sitting somewhere at that sulfate-sulfide buffer. Yeah.
So you see a lot of anhydrite in there, because
Yeah.
basically.
Yeah, and epidote, magmatic epidote as well is present. So there's definitely a huge change in FO2 happening at some stage, and we see co-entrapment. Not in the Bousquet rocks yet, but in the MIC rocks we see anhydrite trapped.
That's the pluton.
That's the pluton. Yeah.
That's what I expect to see.
Okay, very good. All right, well, thank you very much.